Assignment 6-7, question number 1. Let's not waste time. Let's get to this. This is a review assignment, and so far this is the most important assignment you've done. So can you integrate v cubed subtract 4v plus 1 dv? Just the antipower rule. I know you can do it. So the answer to this would be add 1 to the exponent and divide. Add 1 to the exponent and divide. The antiderivative of 1 is 1v, and then don't forget the constant. Done. Number 2. Can you integrate x subtract 1 squared, x to the exponent 3/2 dx? The first thing I kind of notice here is that it's reasonable to do some algebra to make this simple. The numerator I can expand, so I'm going to do that. So when I expand the numerator, that's foiling. That's what it's going to look like. And then I'm going to take the denominator, which is a monomial, and I'm going to divide it with each term to make it simpler yet. And I'm going to use the exponent rule. So I'm going to go 2 take away 3/2. That's 1/2. Oops, I'm still integrating this, parentheses. -2, subtract the exponents, that's 1 take away 3/2, that's -1/2. And then 1 over x over 3 would be a negative exponent. So instead of 1 over, I could write it with a negative exponent, close it dx. All right, so there's some algebra. Now, each one I'm going to do the antipower rule, which is add 1 to the exponent. So 1 plus 2, that's 3, and then the reciprocal. Here, add 1 to the exponent, so -1 plus 2 is +1/2 times the reciprocal. And then the last one, add 1. So -3 plus 2 is -1/2, and then the reciprocal, and then the constant. Done. And don't worry about simplifying that at the end. Number 3. Integrate y squared, y cubed, subtract 2 to the exponent 5 dy. So what I look for here is this the anti-chain rule. Take the derivative of the base. Does that derivative, does it match in terms of the type of term it is? Do the terms match? And so the derivative of this is 3y squared, and this is 1y squared. So they do match. So we're going to go 3y squared. That's the derivative of the base. And then I need a fraction to keep them equivalent. So if I go 1/3, that keeps these equivalent. Then circle the hook and unhook it. And my answer is 1/3. Add 1 to the exponent, and then divide or times the reciprocal, and then you have your answer. And don't forget the constant. Number 4. In number 4, I'm going to write it calculus friendly right away. So I'm going to write it as x times 4 subtract 3x squared to the exponent -1/2x. So we need that skill. So the square root in the denominator can be written with the exponent 1/2. Because it's in the denominator, it's be -1/2. The derivative of the base is -6x. That matches in terms of they're the same term as x. So I can do that. So I'm going to go -6x. And I need -1/6 in front. And now I just unhook it. So -6x, I unhook. So my answer is the -1/6 in front. I have 4 subtract 3x squared, add 1 to the exponent. -1 plus 2 is +1/2, and then the reciprocal, and then the candy, and it's over. I don't need to simplify that at all. Number 5. Number 5, we're integrating from -4 to -1. This is different because this is a definite integral because it has limits, it has bounds. For absolute value, to find this, there's no antiderivative to absolute value. We need to graph it and find the area. That's another way to find the definite integral, is area. So we're going to graph this. Oops. I didn't really mean to put it there, but I'll put it right here. From -1 to -4. I'm going to sneeze. I hope I don't. Oh wait, so -1 to -4. So if I plug -4 in here, 2 times -4 is -8 plus 6 is -2. But the absolute value of -2 is 2. So I have 1 point there at -4, 2. Plug -1 into the function. That's -2 plus 6, which is 4. So this is going to go up to 4, -1 and 4. And the last thing I need to find is the vertex. So to find the vertex, take what's inside the absolute value bars, make it equal to 0, and solve it. And you can see the vertex is at -3 and 0. And then you can make your v. That's what the picture looks like. To integrate this, we're going to find the area under both. That means there are two triangles that we're going to find the area of to get our answer. So the first triangle, the area of a triangle is half the base times the height. And then the second triangle, half the base times the height. And you have the answer. If you simplify this, it equals 5. Perfect. Number 6. In number 6, I'm integrating t and the square root of t plus 1. So already I know I need to write that as the exponent 1/2. If I take the derivative of the base, the derivative of that is +1. It does not match the term in front, which is t. They're unlike terms, so I'm going to use u substitution. So I'm going to let u equal t plus 1. I'm going to get t by itself by subtracting 1. And then take the derivative of both sides. So then I have the values I need for u substitution right there. Come back to the integration question. T is u minus 1. T plus 1 is u. And then dt is du. So now we have a situation where I can do some algebra and then do the Antipower Rule. So remember the exponent is 1 here. So when you multiply it, you're going to add the exponent. So that's 3/2 when you add it up. And then -1u to the +1/2. So a little bit of algebra. Now we're ready to do the Antipower Rule. So add 1 to the exponent and then the reciprocal. Same thing here. Add 1 and then the reciprocal. And then don't forget the constant. And then the last step here is to plug what u equals back in. So we know u equals t plus 1. So then that goes back in for the final answer. Done. And that's your answer for the integration of that. That's what's called u substitution. All right, number 7. Number 7 is the fundamental rule of calculus, the sequel, part 2 here. And this part of the fundamental theorem of calculus is that derivative and integration undo each other. So when you see derivative and integration, this is so this should be x cubed. This is a substitution question. So you substitute in the upper bound. That's 2x plus 1. Cosine of that. So the cosine of 2x plus 1, subtract the cosine. Now plug in x cubed. That's 2x cubed plus 1. What you have to be concerned about after the substitution is the hook on, if there is one. So the upper limit, the hook on, the derivative of x is 1. So that doesn't change anything in terms of multiplying by 1. But the lower bound, the lower limit, the derivative of x cubed is 3x squared. So it's that hook on that comes from the bound that you have to be careful about. So it's the top, subtract the bottom, and then there's a hook on factor that you have to be aware of. So there's your answer. Number 8. Number 8 has multiple parts to it. We'll get through it together. So you're given the velocity is t plus 4. And it's the square root of t plus 4. Right away, I'm going to write that as t plus 4 to the 1/2. It gives you a restriction. T has to be greater than -4. Otherwise, if it's smaller than -4, it would be undefined. It would be imaginary. So that's why they have that restriction there. Part A says, find an equation for the acceleration. So that's the derivative of the velocity. So just take the derivative of it, which is just the power rule, and then write it down. So the derivative of this, 1/2 times -1, subtract 1 to the exponent, and it's done. Part B, an equation for the position. Now, to find the position, you're going to integrate the velocity. So let's see how we would do that. So to go the other direction, we're going to integrate the velocity to find the position. To integrate this, the derivative of, here, let me write this down. We're just going to put the negative in front of the integration sign, which you can. The derivative of the base is 1. So I just need to do the antipower rule with the negative in front. So add 1 to the exponent. And then the reciprocal. And then plus c. In the question, it gives you, so there's the one, and they said y equals for the position, so I'll write it as y equals. Then it gives you a value. It says that y at 0 equals negative 10/3. So if they give you a point on the position, so in other words, at 0 seconds, or like the initial position of the object is negative 10/3, we plug in negative 10/3, and then the time is 0. And then we can solve for c and not have a c in my answer. So to simplify this, 0 plus 4 is 4. 4 to the exponent 3/2. The square root of 4 is 2, and 2 cubed is 8. This is negative 16, so I'm going to add 16. That was negative. And then if I simplify this, it's 6/3, which is just 2. So put it all together, and you have negative 2/3 t plus 4 to the exponent 3/2 plus 2. We just found that value for the constant. So that's the position equation for part B. Part C says, now that you have that, what's y at 5? So without a calculator, if you plugged 5 in, could you simplify it if you had to? So I'll help you through that. So plug 5 in. What's the position at 5? So this is 9 to the 3/2. So 9 to the 3/2. The square root of 9 is 3, and 3 cubed is 27. 3 goes into 27 9 times, and then negative 18 plus 2, so the position is negative 16. Part D. V at 5, the velocity at 5. So find the velocity equation again, and then plug in 5 for the velocity equation. So for the velocity equation, there it is. Plug 5 in. That comes right here, right from the beginning. Plug 5 in for t. So 5 plus 4 is 9. And the square root of 9 is 3. So this answer is negative 3. Part E says the acceleration at 5. So use the acceleration formula we just came up with in part B, or A, I mean. So that's negative 1/2, 5 plus 4 to the negative 1/2. See if we can simplify that. So that is right there. This is the in part A. That's the acceleration formula. So just plug in 5 here and simplify it. That's what this is. So 5 plus 4, that's 9. And then the square root of 9 is 3, but the negative exponent makes it 1/3. So if you put it together, you get negative 1/6. I want you to notice that the velocity and the acceleration are both negative at 5, which means the direction it's going, in this question, it's vertical direction, so the negative makes it going down. This is how fast it's going down, and the acceleration's negative, so because the signs match, the object is speeding up as it's going down. F. Last one. What's the speed at 5? So speed is the absolute value of velocity. So we already found that the velocity at 5 is negative 3. So the absolute value of that would be positive 3. And that would be the speed and the connection there. That's number 8. Number 9 is a calculator question. So you need to press pause and get your calculator out. So I'm going to do that too. So we're given an equation, the velocity. Use a calculator, and there's 4 parts. So because there's 4 parts, I'm going to show you how to make this a little simpler. So with your calculator, you're going to define the velocity in your calculator to make it easier to calculate as you go through. So, to define it in your calculator, you're going to press the shaky calculator. You're going to get to the graph part, and then you're going to press tab, and then you're going to go control, divide, and you're going to type it in. So you're going to type in. Now, we're not going to type in t, because it's not in terms of t. I've never tried this. Like, what would happen if you changed that to a t? Let's see. What would happen if you went t? Would it like get angry at you or not? I'm going to try. So if it gets angry, I'll change it to x. So t subtract 1, and then in the denominator is t squared plus 1. Okay, let's see what happens. It might be angry. I don't know. No, I didn't like it. See, it got angry. So let's just erase that. I just tried it. So change it back to f at x. So it's all going to be in terms of x. So change that to x. Then we'll do it again. So control divide and then type it in again. You're just going to go x subtract 1. And then the denominator be x squared plus 1. And now it'll be happier. Because the variable, there's an interesting graph, but it's not the graph I care about. It's that you defined it in your calculator. Now make sure you remember that's how you defined it, f1 at x. So now I'm going to press the shaky calculator button again to go back to calculate. That's that button right there, you know, right there on the top left, that shaky calculator button. And then I'm going to start answering the questions. So now that I've defined it. So the first question is, what's the velocity at 2.3? So just plug in 2.3. But the good news is, because you've already defined it as f1 at x, I type in f1 at, and I just type in what I'm looking for. So I want to know 2.3. That's it. Control enter, and you have your answer. So it makes it a lot simpler if there's multiple questions on the same equation. Define the equation, and then it's a lot quicker to work with our calculator. So the answer here for A, what's the velocity at 2.3? And the answer is 0.206. You can just truncate. In part B, it says, what's the acceleration at 2.3? Well, acceleration is the derivative of velocity. So I need to take the derivative of what I just defined. So menu, calculus, and we're going to do derivative at a point. So press 2. And so the variable's x, and at what value are we taking the derivative? At 2.3, press enter. Then inside, type in f1 at x, and then you have it all set up, control enter. And so once you define it, it makes it a lot simpler to work through. So the acceleration at 2.3 is 0.007. Remember, you don't have to round. You can just truncate to 3 numbers after the decimal. Part C asks, what's the displacement? So define displacement, that's an integration question from velocity. If you integrate velocity, you get displacement. So we're going to integrate from 0 to 3, and we're going to integrate the velocity. Now, it's already been defined to make it easy again, but that's what I'm doing. I'm integrating from 0 to 3 the velocity to get displacement. So on my calculator, I'm going to go menu, calculus, integrate from 0 to 3, and then I just type in f1 at x. So f1 at x, and then move the cursor, dx, and then control enter, and that gives you the displacement. So negative 0.097. In part D, it asks for the total distance. Now, total distance and displacement are almost the same, except for total distance, we're going to do the absolute value to get the answer. So this is total distance, and this is displacement. So almost the same thing. I'm going to come back here. Again, I'm going to press menu. I'm going to go calculus and integrate from 0 to 3. I just have to know where the absolute value bars are. So if you look at right beside the number 9, let me turn it sideways here. So right beside the number 9, this button here is what gives you absolute value. So we'll do that. And then you see a bunch of functions that pop up. You want to highlight over this one that has the bars and press enter. Now those are absolute value. Now type in f1 at x, move the cursor at dx, control enter. And there you go. That, again, is the total distance traveled. So that's 0.779. in part, and that's all the parts, right, to number 9. All right, let's look at number 10. So in number 10, you have a graph. And it's a rate graph. It says show an integral setup for the average density of hikers between 1 and 5 miles. So the average density is another way of saying average value. That's an integration question. So we're going to integrate from 1 to 5. And we're going to integrate this rate function, which is d at x. So we're going to write it as d at x dx. And then we're going to divide by the difference in the limits or bounds. So this is what it looks like. So you have the integration, and then it's divided by the difference of the bounds. That's the setup to find average value, or this is average density, which means the same as average value, just connected to the story. In number 11, we're going to actually find a value for this, doing it a few different ways. So in number 11, use a midpoint Riemann sum with n equals 2. So if I go from 1 to 5, the common width is going to be 5 take away 1 divided by 2. So I subtract the bounds, 5 take away 1, and we have 2 rectangles. So the width of each rectangle is going to be 2. If I look off the graph from 1 to 5, so if it has a width of 2, you're going from 1 to 3, the mid value is at positive 2. So the height of the first rectangle is 35. And then the height of the second rectangle, midpoint, would be 4, would be at 25. And then again, you're dividing that by 5 take away 1, which is 4. There's no need to simplify it unless you had to. So this is the same work as number 10. We did the integration by doing a Riemann sum of 2 rectangles, and then we divide it by 4. If you reduced it down, you would get the answer 30, and it would be 30 hikers per mile. It would be the answer. That's using a Riemann sum. In number 12, it says to use a trapezoidal sum. So if you do a trapezoid, we're using 4 trapezoids. So now the width of the trapezoids, we go 5 take away 1 divided by 4 instead of divided by 2. So 5 take away 1 divided by 4, that means the width of each trapezoid is 1. So the formula is 1/2 times the width, which is 1. And then we look at each height to plug in. So we're going to plug in 40, 35, 30, 25, 20. The first height is singular. All the middle heights are doubled. So 35, 30, 25, they're all doubled. 20, again, is singular. That's called the trapezoidal rule. I don't have any desire to simplify it, but this answer is in hikers per mile. So, and we have to divide that answer by 4, just like I did before. So we're finding different ways to integrate, and we're going to divide by 4 whatever the answer is. So you take that answer divided by 4, and that gives you the answer for the average hikers per mile using the trapezoidal rule. For number 13, estimate where on the trail the density of the hikers is equal to the same average density for number 13. So when I look at that, let me make sure I'm doing that. Where would that be? So we do have to simplify then to understand the number was 30. So if I look at 30, at which one did it equal? 30, the answer is at 3 miles out. So the average was 30 hikers per mile. Even for number 12, it's simplified to 30. So where does that occur? At 3 miles, right? At 3 miles from the trailhead, right? Is that what that is? Or the density, yeah, from the trailhead. So at 3 miles from the trailhead, right? The average equals like what it is. Number 14, let me just write it out. So at 3 miles from the trailhead, the average density of hikers is equal to the density of hikers. So we found the average, and where does that occur? At 3 miles out. Number 14. So let's look at number 14. Write a complete sentence using numbers and units to tell what does it mean from 1 to 5 when you integrate from 1 to 5. So when you integrate from 1 to 5, what does that mean? And so we're just going to write that down. The integration from 1 to 5 dx mean is, so when you integrate a rate, what you're left with is the unit of what you're left with. So in this case, hikers per mile, you integrate it, you're just left with hikers. So in other words, you're left with how many hikers there are from 1 to 5 miles is the number of hikers. Of hikers 1 to 5 miles from the trailhead. So what does it mean when you integrate a rate? Whatever the unit is that the rate is in, that's what the answer is going to be. It's an accumulator. So it accumulates how many there is of that unit. So in this case, it's hikers. So when you integrate it, it tells you how many hikers there are from 1 to 5 miles from the trailhead. When we use the estimation, there's about 30 hikers between 1 to 5 miles from the trailhead. That's what we used it for. All right, number 15. Next page. If the graph of f at x, so a totally different question. If the graph of f at x is concave up from A to B, I'm going to just draw that. A to B is concave up. Does the trapezoidal rule give a value larger or smaller than the actual value of that? And the answer is, for number 15, if it's concave up, let's see, I'm going to actually draw it a little different here, so you can actually really see it. So here's something concave up from A to B. If you do trapezoids, will this trapezoid be above or below? Now, if you draw it really subtly, you can see that if you connect these, it's going to be above the actual curve that's concave up. Because of that, the answer here is that the concave is going to be larger, or we would say it's an overestimate, right? Now, what would happen in the second question is what would happen if it was concave down? Is that right? So for number 16, it says if the second derivative is less than 0, what does that mean? That means concave down. Does the trapezoidal rule give a larger or smaller value for that integration? So it's the same question asked a different way. So the second derivative is less than 0, which means concave down. What would happen? So if I draw a really subtle concave down, I'll show it to you. If you do trapezoids and it's concave down, will that be an over or underestimate? So if you find 2 points and you connect them, I want you to understand that concave down for a trapezoid would be an underestimate. It would actually be different if it was a rectangle. It would be an overestimate. But for a trapezoid, it's an underestimate. It's really subtle, but it's under the curve. So for this one, it's going to be smaller if it's concave down. And for this one, it's going to be larger if it's concave up. And we call this an overestimate, and this is an underestimate to do with concavity. So sometimes in an AP exam, you have to justify if something's an overestimate or an underestimate. And what they're looking for is if you're looking at the concavity. Tells you that. All right, number 17. The second derivative is equal to 0. What must be true about the value found using the trapezoidal rule and the actual value of that from A to B? So the second derivative is equal to 0 on that from a to b. What would that actually tell you? And what the answer is for number 17, what must be true about the value is that all the values must be the same. So the second derivative from a to b, if there's no concavity, so no concavity would mean that all the values are exactly the same. So what would be an example of that? Like a line has no concavity. So it's not an overestimate or an underestimate, it's exactly what it should be. So let's say I have a line has no concavity. If you do a trapezoid with a line, what do you notice? Is that it's not above, it's not below, it's exactly the area you need. So that means it is really what they're asking, is it an over or underestimate? And it's perfect, right? It is not. The values are the same. What was it say? Yeah. So that means that if there was no concavity, the trapezoid gives you the exact answer. It's not over, it's not under, it's exact. If these were rectangles, it would be different, right? But for a trapezoid, it has no concavity, it's the exact answer. It's not overestimate, it's not underestimate. Number 18. Set up, but don't integrate, an integral which could be used to find the area bounded by these graphs. So I need to graph them. So negative x squared plus 1. Can you graph that? I'm going to do it. I wonder if you can do it as I'm doing it. And then x squared subtract 2x subtract 3. I'm actually going to factor that. So x subtract 3, x plus 1, and then I'm going to find the x-intercepts. So I have an x-intercept at 3 and another one at negative 1. So can you find 3 and negative 1? I'm also going to make them equal to each other to know where they intersect. So negative x squared plus 1. I don't even need to know that really, right? 1, 2, 3. I'm just sketching. And in terms of the limits, though, I do need to know it for the limits. So I am going to make them equal to each other so I can find the limits. All right. So negative 1 and 3, and it kind of does this. And then I have this area. So the first thing I'm trying to look at is which one is above and which one's below. So the parabola concave down is above. So when I integrate this, the first one is negative x squared plus 1 because it's above, subtract below, which is x squared subtract 2x subtract 3. So there's the setup, which is above, top, subtract bottom. I need to find the limit, so I make them equal to each other to find it. I kind of ran out of space here, so I'm going to do it over here. I'm going to combine like terms. I'm going to add x squared. We have negative 2x, and I'm going to subtract 1, which is negative 4. I'm going to divide everything by 2, and then this is negative 2 and positive 1. So this is the upper limit, and this is the lower limit. So it goes from negative 1 to positive 2, and it's top subtract bottom. That's the setup. All right, number 19. In number 19, it says sketch the region bounded by, so the square root of x subtract 2. So we're taking the square root and moving it 2 to the right. So move it 2 to the right and sketch it. Right? So move it 2 to the right and sketch a square root. The second one is the line x equals 6. So there's 2, 3, 4, 5, 6. There's the line. X equals 6. And then what's the third one? Y equals 0 is the x-axis. So y equals 0. And then can you shade in the area between the square root, the line, and the line? That's what it's asking. and then it says find the area of it. So to find the area of that, it's top subtract bottom, or just the top. The bottom is 0, so that it's just the square root of x subtract 2 from 2 to 6. And normally you would go subtract bottom, but the bottom is 0. So it's just this. What's the area under the curve with the x-axis? And it's bounded by 2 to 6. And it's just that function. I wrote it calculus friendly. To find this area, you add 1 to the exponent. That's 3. And then the reciprocal. And then it's from 2 to 6. Plug in the upper bound. Now, when you plug in the lower bound, 2 take away 2 is 0. So 0 to whatever times whatever, that answers is 0. So I don't need to simplify that. Here, this is 4 to the 3 halves. So the square root of 4 is 2, and 2 cubes is 8. And so the area here is 16 over 3. For number 20, I think we're using the same sketch for number 20, so I might re-sketch it for you. For number 20, use the same one, but find the volume of a solid formed by using square cross-sections. So I'm going to do the same graph. And it's square cross-sections perpendicular to the x-axis. So that's the same region of that square root. So think about the base of the square coming out at you is right there. And so what length is that base? It's just top subtract bottom, which is 0. So it's just that curve, which is the square root of, what do we just do? X subtract 2. So I'm going to write it calculus friendly. So that represents the length of the base at any moment there. So this is an integration question for volume. And we're going to integrate from 2 to 6. And the formula for area of one of the squares is take the base and square it. And then we have a value to put in, an algebraic expression for that base, which is x subtract 2 to the 1/2. And we're going to square that. So you take the base and square it. Now you know square root and square, they undo each other. So it's just x minus 2. So add 1 and divide, and negative 2 is negative 2x. And we're integrating from 2 to 6. Then plug in the upper and lower bound. So the upper bound, we plug in 6. The lower bound, we plug in 2. This answer is not 0. And then if you had to, you could simplify this. 36 divided by 2, that's 18, take away 12. 4 divided by 2 is 2, take away 4. So this becomes 6, subtract negative 2. So that volume, I think, is 10 if I did it. Or what did I do wrong? 6 subtract negative 2 is, see, I did everything right. That's where I made the mistake. Everything else is perfect. That's my life, right? Did you ever find that? That the more difficult math you're doing, and then when it gets to this, then you make the mistake? Silly. All right, 21. So I think we're taking the same region in 21, but we're doing something else. So we're going to take the same, set up the integrals, but don't find the volume, which could be used to find volumes. So we're still taking the same sketch. So let me sketch the same one. And we're going to revolve it around the x-axis. So that's with dx. So if I revolve that around the x-axis, it's pi. Again, it's going to go from 2 to 6. So from 2 to 6, we're revolving it around a horizontal line. It goes top to bottom revolving. And then the radius is the same as the base. So this base that we had for a square is really the radius if I rotate it all the way around. So the radius is the square root of x subtract 2. And there's your setup to find the volume, pi r squared, from 2 to 6. The next one, part B, is a line. So this one for part B, revolving around y equals 4. So if I put y equals 4 here, there it is. That's above here, somewhere above. It doesn't really matter where, how far above, but it's above the area. Can you describe which would be the outer? Since there's a space here, this is a washer. So I need to know the big radius. So that's from top all the way through the bottom. What represents the big radius? So that whole distance is just 4. So the big radius is just 4. So again, the beginning part where you integrate from 2 to 6. So the big radius is 4. Subtract the small radius. So what would represent the small radius? Remember, it's the line of revolution to the front of the area. And we're going to go top, subtract bottom. Well, the bottom is a curve, so it's 4 subtract the square root of x minus 2. And you have the setup for the washer method. And that there, 4 subtract the curve, is the small radius. So the big radius subtract the small radius. All right, number 22. This is a completely new question. The base of a solid is the region bounded by y equals 1 over root x, x equals 1, x equals 4, and y equals negative 3. So let me guide you through the sketch because you need to see the graph of this. So I'm going to use, so we have 1 and 4. So 1, 2, 3, 4. So I'm going to focus on 1 and 4 because those are my bounds. So if I plug 1 in, 1 divided by the square root of 1, the answer is 1. Oops, right here. And if I plug in 4, the square root of 4 is 2. So it ends up being 1/2 here. So it's decreasing here. So 1 gives you the answer 1, 4 gives you the answer 1/2. So at least you have the endpoints, connect them with the curve, and bounded by y equals, what's the y equals? So this is region bounded by 1, 4, and y equals negative 3. So y equals negative 3 is down here. So we have this. We have this. So we have x equals 1, x equals 4, y equals negative 3, and the curve. And I'm supposed to find the area there. Now, this area underneath the x-axis is just a rectangle. So if I just want to find the area, that's super, super simple. So it says, all right. So we're using rectangular cross sections, so we're not finding the area, the volume, whose base is in that region and are perpendicular to the x-axis, so everything's in terms of x. So already I know I'm integrating from 1 to 4. No pi, it's not a circle, it's rectangles. And it says the heights are 3 times their bases. So if I just understand that it's base times height is a rectangle, and the height is 3 times the base, if I put this together, just to get a sense of it, to simplify it, it's just 3b squared. So again, the height is 3 times the base, and then simplify it. What would represent the base here is top subtract bottom. So the top is 1 over root x, and then subtract the bottom, which is negative 3. And yes, subtracting negative is adding. So we're just going to write that in. It's 3. The base is 1 over x, subtract negative 3. And then there's the setup, and it's done. And that's using the area formula, 3b squared, and that represents the base, which is top subtract bottom. All right, number 23. We're almost there, right? No, we're not almost there. There's another page. I can do this. So these are just graphing questions. Number 23. So if I look at question number 23, use the graph y equals f at x shown at the right to graph problems 23 through 26 without using a calculator. So if I want to graph this, understand the key points and what's happening. So if y equals f at x, y equals f at negative x plus 1, what's happening and how can I figure this out? So I have points at negative 2, 1. I'm going to write them down. So negative 2 and negative 2. Another point that may be important, it's only for absolute value it might have an effect. So for negative 2, negative 2, the other point I'm going to change is at 0, 2. Another point I'm going to change, if I understand, is at 1/2 and 1, because there's a point of inflection at 1/2 and 1. And then I have like that curve that kind of curves down. So I'll use 1, 0 as well. And then see if I can put all the pieces together. So this is just graphing practice. So those are the key points. So what's inside the parentheses affects the x. So divide the x by negative 1. So it's the inverse. So that becomes positive 2, stays 0. That becomes negative 1/2. And that becomes negative 1. So every x value divide by negative 1. The y value, just add 1 to it. So that's negative 1, that's 3, that's 2, and that's 1. And those are the points we're going to use to graph. So now draw the graph using those points. So we have 2 and negative 1. We have 0 and 3. We have negative 1/2 and 2. Oops, here we'll say that's negative 1/2. So negative 1/2 and 2 and negative 1 and 1. So what would this graph then look like? So these connect as a point, as a line, just like that. And then there's a whatchamacallit, a point of inflection right here. And then it looks like a cube root going across. All right, that was 23. 24. What would happen to the graph if this happens? So when the absolute value is on the inside, you only graph the right side and reflect it. And then times 2 means you take every x coordinate and divide it by 2. So if I only look at the right side, if you see 0, 2, take the x coordinate and divide it by 2. That stays 0, 2. If I look at 1/2, 1/2 and positive 1, when you divide by 2, it becomes 1/4 and positive 1. If I look at the next point, like 0, 1, 0, it becomes, divide by 2 becomes 1/2 and 0. And so let's look to see what that would look like. So I'm only graphing the right side using those points. So it still starts at 0, 2, then at 1/4 and 1, and 1/2 and 0, it has this kind of feel to it. And then it gets reflected on the other side. And then it completes. Kind of weird, right? Just go with it. All right, that's 24. 25. we have y equals negative 1/2 f at x. So all that does is affect only the y-coordinate, and it's a reflection down or a reflection up. It's across the x-axis, and all the y values are split in half. So I'm going to take this y value here, which is, it's at -2, -2. So the x-coordinate stays the same, but the y-coordinate you divide by -2. So that becomes +1. Use this point up here, 2, 0. Same thing. The x stays the same, and the y will stay the same. Because when you go 0 divided by -2, it's still 0. Or times, divided by -2, it's still 0. This point of inflection, which is at 0, which is at 1/2 and 1, the 1/2 stays the same, but when you divide it, it now becomes -1/2. And I'm just going to curve down from there. If you took 1, 0, and it would stay 1, 0. Wait a second, 0, 2. This one is 0, 2. So if the y-coordinate's 2, divided by -2 would be -1. So I made a mistake there. So it's 2, -1. 0, -1. All right, let's graph this. So we have -2, -2, 1. 0, -1. 1/2 and -1/2. Like that. And then connect it from there. And at 1, 0. Doop, boop, like that. I know. Just keep powering through it. 26. Last one like this. What do the absolute value bars do on the outside? It makes all the y values positive. So this point will be, all the negative points will be reflected up, and has been shifted 2 to the left. So can you shift all of this 2 to the left, and anything below gets reflected up. So if it's 2 to the left, it's now going to be at -4 and +2. 2 to the left, -3. 2 to the left will be 2 to the left. So this is going to first look like a V, and then so it's going to look like a V, everything. Remember, this part was below, right, and got reflected up. So everything's been shifted. And then the next part, here you have that cube root looking thing. So just redraw it. And make sure that this point right here at 1, 0 is at -1, 0 now, 2 to the left. So when I draw it, it's going to kind of look like that. So it has that curve, and then it doesn't curve below, so it was curving down here, but it's got reflected up, so that's what it looks like. All right, you got to let it go. 27, it's going to be okay. All right, g at x is equal to the cube root of x subtract 1. Find the inverse and graph them together. So to find the inverse and then graph them together, it's just a pre-calculus question. To find the inverse, x and y have been switched, and then solve for y. So we're going to cube it and then add 1 to get y by itself. Oops. That's the symbol for inverse. So if you cube and then add 1, y is by itself, so that's the inverse of this. If I graph this, this is a cube root, 1 to the right. So this is what it would look like as a cube root, 1 to the right. This is a cube up 1. So a cube up 1, you'd start at +1 and curve up to the right and down to the left. And notice they reflect along the line y equals x. That was 100 years ago, right? You should look at your notes. For inverse from like a year ago. Done. All right, for problems 28 to 31, can you find the discontinuities and label them as removable or non-removable? So for 28, this is called greatest integer function. So at every integer, there's a discontinuity, there's a jump. So at every even number, there's a discontinuity, and it's all non-removable because the limit doesn't exist. So at every even number, there's a discontinuity, and that discontinuity is non-removable. Do you remember the step function that kind of looks like this as you would graph it? So at every even number, there's a step, and because the limit doesn't exist, it's non-removable. 29. So look at the denominator and factor it. That's x plus 3, x subtract 2. And so notice that they're not removable after you factor it. So at x equals negative 3 and positive 2, we have discontinuities. And those discontinuities are non-removable. The limit does not exist there. And ultimately for this, they can't be removed. That's like the visualization of it. Number 30, looking at the denominator. H at t, the square root of t. Now the denominator is t plus 3 and t subtract 3. And so where are the discontinuities here? Understand the domain restriction, right? So first of all, the domain restriction here is that t has to be greater than or equal to 0 to begin with. And then because of that domain restriction, at negative 3 is not even in the domain restriction. So the only discontinuity is at t equals positive 3, and it's non-removable. So the limit doesn't exist there. So negative 3 doesn't count because it's not in my domain. But positive 3 is a discontinuity. It's non-removable. You can't remove it. The limit doesn't exist there. Number 31. So at 31 we have piecewise. So we have x subtract 2. X squared plus x subtract 6, and then 0. And the question is, where are the discontinuities? Here. And so a couple things to look at. So first of all, we already looked at this denominator, and so this denominator was x plus 3 and x minus 2. Now, in this situation, you can actually remove x subtract 2. So there's a discontinuity, but what's left over is, so at x equals 2 is a removable discontinuity, because you can take x minus 2 and you can remove it. The other discontinuity is here. And notice 2 also represents where the break in the two graphs are too. There's like a jump there. So it's still there. It's a removable discontinuity there, so that's good. At negative 3 would be another one. And at negative 3 is a non-removable discontinuity. The limit does not exist there. All right, number 32. We're getting there, I promise. Fill in the blank with the number to make that continuous at x equals 2. So all I need to do is plug 2 in, plug this 2 into the top, and 2 take away 2 is 0. So 0 divided by that, the only number there that would make it continuous is 0. That's the answer to number 32. Because 2 take away 2 is 0, divided by who cares is 0, If this was 0, it would make it a continuous function. Number 33. Find the values which make that continuous. So plug -2 in to the top, and plug -2 into the bottom, and there's one equation. Take +1 and do the same thing. So plug +1 into the top, and +1 into the bottom. So for continuity, at -2 and at -1, so as x approaches -2, what's the name of this function? F at x. So what we're showing for continuity is the limit of f at x from the right is equal to the limit as x approaches -2 from the left. So that is continuity. And for +1, we're showing the same thing. So +1 from the right and +1 from the left. If that's true, then this is continuous. So if the right side equals the left side and so on, this is what we're showing for continuity. So we have two equations and two unknowns. So on the left, 1/2 times -2, that's -1 plus b. On the right is 4a. On the left here, this is 1/2 plus b. And then on the right is just a. I can actually subtract them the way I see them. So I have -1 take away 1/2. The b's would cross out, and then 4 take away 1 is 3a. To get a by itself, divide. So divide by 3 1/3, and notice you get the answer -1/2. Checking the answer key, make sure I'm good, which I am. So a is -1/2. Go back to either equation. I'll go to the top one and plug in -1/2 for a. So I can solve for b. So this is -2. Add 1. So b is -1. So when a is -1/2 and b is -1, they would be continuous, those piecewise functions. All right, number 34. For number 34, find the values which make it continuous and differentiable for a and for b. So first we're going to plug 1 in. So if I plug 1 in, this is what it would look like. Plug 1 into the top. Oops, that's a subtract sign. Make it equal and plug 1 into the bottom. So I plug 1 into the top, 1 into the bottom, make it equal to each other. Then I got to take the derivative here. So if I take the derivative of that, the top derivative is 3ax squared minus b, no 7. The bottom derivative is -2bx plus 3b. And again, I need to do the same thing. I need to plug 1 into the top and 1 into the bottom. So I take the derivative. I'm going to do the same work. Now simplify the top here. This is a subtract b plus 7, -b plus 3b. So combine like terms here. Notice that I can just cross out the negative b's. So I have a plus 7 equals 3b. That's good enough for now. I'm going to do the same thing here. I'm going to plug 1 into the top and 1 into the bottom. This is just all algebra. So that's 3a times 1 squared. Take away b. Make it equal to, plug 1 into the bottom here. So that's -2b plus 3b. If you plug 1 into the x here in the denominator, combine like terms again. So I have 3a is equal to, this is 1b, so add 1b, that's 2b. So I got 3a is equal to 2b. So now I got two equations that I have to solve. I'm going to multiply this times 3 There's more than one way to do this. This is the way I'm choosing to do it. So multiply the top times 3, subtract, you get 21 is equal to 7b, divide, so b is equal to 3. Take that answer, I'm going to go in here, so that means 3a is equal to 2 times 3. So that means a must be equal to 2. So b is equal to 3 and a is equal to 2. That would make them both continuous and differentiable. All right, number 35. So if y equals that, find the second derivative. So I'm going to write it as 3x to the negative 1 minus 2x to the 1/2, and I'm going to find the second derivative. That's what it's asked for. So the first derivative is negative 3x to the negative 2. 1/2 times 2 is negative 1, and then subtract 1 to the exponent. To find the second derivative, again, negative 2 times negative 3 is positive 6. Subtract 1 to the exponent. Negative 1/2 times negative is plus 1/2, and then subtract 1. And you get the answer. Number 36. We're so getting closer. I promise you. Hopefully you're not doing this in one sitting. Give yourself a little break. 36. Can you take the derivative implicitly? So far, this is the most important review assignment you've done yet. It goes through all of it. So to do this implicitly, this is going to be 6x. The derivative of this is negative 4y, but it needs hook y prime. This is the product rule. The first times the derivative of the second times the derivative of the first, and 20 is 0. Gather up the y's. So I'm going to subtract 4y, and I'm going to add 4y y prime. So I'm going to bring the y primes together. If it doesn't have a y prime, it's going to be moved to the other side. I'm going to factor out y prime. So I have 4x plus 4y. And then the last step is to divide. So it's 6x subtract 4y, and then it's divided by 4x plus 4y. That is the derivative. Now, I think there's questions connected to it. So 37 says, find the points where there's vertical tangents. So make it, a vertical tangent means it's undefined. So take the denominator and make it equal to 0, and then find where that's true. So make the denominator equal to 0. So solve for y. So subtract 4x and divide. So when you divide by negative 4, y is equal to x. Go back to the equation and plug in x for y. So wherever there's a y, plug in x. And then we're going to solve for x first. So that's what it's going to look like if you plug in x for y. So subtract, that's 1x squared. This is 4x squared. So just keep combining like terms. I'm going to, what did I do here? This should be negative 4. Why is that negative 4? Oh, because I'm plugging in negative x. Ha. I made a mistake here. So if you subtract it, there's a smudge there. This is negative x. So that doesn't affect here, but that affects this to be negative 4x squared, or else I was going to get an imaginary answer. So now when I add 4, I have 5x squared is equal to 20. Divide by 5. And then when you take the square root, the answer could be either positive or negative 2. So now I have two x coordinates. And then I don't have to be too complicated. Know that the y is just a negative x. So for positive 2, or that whatever the x is, you change the sign. So 2 and negative 2. And the other one would be negative 2 and positive 2. So that here just tells you, if you know the x coordinate, just change the sign for the y coordinate. So at those 2 points, we have vertical tangents. Pretty good algebra, right? All right, I'm super proud of you. You're still sticking with me on this. 38, find the equations of lines tangent to and normal to the graph from 36 at that point. So the word tangent and normal is the derivative. If it's at that point, then we already have the x is negative root 2 over 3, and the y is 0. I need to find the slope. So I already have that. The slope formula, again, was, and if I reduce it down, which might be a little bit easier, divide everything by 2. This is what you get for the slope formula. And then I'm just going to plug in what the value of x and y are. Well, y is 0. So if I plug this in, so y is 0. If I plug this in for x, notice these cross out anyways, right? They divide out and you just get the slope 3 over 2. So the tangent formula would be y equals 3 over 2, and then the x coordinate, we have to change it. So it's plus root 20 over 3, and then the 0. For the normal formula, it's the same thing, but I do the opposite reciprocal for normal, and then write the same thing down. Done. That's the tangent, and that's the normal. All right, we're almost there. 39 is the last question. Find the points in the lines tangent to that graph that are parallel to that graph. Okay, let's break it down. It's not too bad. The word tangent means take the derivative. So if I take the derivative of that, it is 3 times 1/3. So that's 1x squared, negative 2x plus 1. So I take the derivative, that's tangent, and then take that and make it equal to the slope of that line. So y equals x, y would equal positive x plus 5. So the slope of that line is positive 1. So solve for y, add x to the other side, recognize the slope is 1, so make it equal to that. So recognize it so that it's equal to 1. Then subtract 1 to both sides, factor it out, and the x value is at 0 and 2. Now we need to find the points, so then I got to plug those values, 0 and 2, back into the original equation. I'm not going to make you do it. I'll do it for you. So if you plug it back into the original equation, the first one's easy. Plug in 0 and you get 3. 2 gives you the answer 11/3, and I'm not going to make you do it. You just plug that back into the original function. At those points, it's parallel to that. Understanding derivative, slope, make them equal to each other. I can't believe it. You finished the assignment. I am so proud of you. You are a worker. You care about it. You're doing your work, and I'm really proud of you. Mr. G Math over and out.